This video is for radioactivity revision. What you can see here is one of my mind maps, and there is on the Mushroom Science YouTube channel already a video explaining all of this if you just want a quick go over. This is going to be quite an in-depth video with exam questions. Whenever you see this symbol here within the video, you can pause it if you wish to and try and attempt the exam question. There will be answers afterwards. Within P2, definitions do come up and you have to be able to write them. If radioactivity comes up, these are the ones that you'll have to write in depth really. Alpha, they do put on quite a bit, is 2 protons and 2 neutrons. You can say as well it's the same as a helium nuclei, however you cannot say it's the same as a helium atom because a helium atom also has 2 electrons attached to it. So don't make that mistake. An isotope, you can say either elements or atoms with the same number of protons but different numbers of neutrons. You cannot say elements with different numbers of neutrons to protons because there's a lot of elements that have different numbers of neutrons to protons. You have to be specific and say the same number of protons but different numbers of neutrons. Radioactivity itself is just the amount of radiation a substance might emit. Half-life is the amount of time it takes for a radioactive isotope to reach half its activity rate, or you can either say the amount of time it takes for the number of nuclei to halve. Either is acceptable. They do like to put that one on. Ionization or ionizing radiation is radiation that can knock electrons off of atoms and change them into ions. I'll go into that in a bit more depth in a bit. And background radiation is radiation that is all around us all the time. We can't do anything about that. A simple introduction to decay. I like to use the analogy of a plastic carry bag before you had to pay for them. Other carry bags are available, of course. They got really, really thin and quite cheap, really. So I like to liken that to a unstable nuclei. Now, some atomic nuclei, mainly isotopes, are unstable, and they undergo a process called radioactive decay. When they do this, the nucleus will randomly, now randomly is really important, they don't know when to do it, it's not a time, it just happens every so often. And it loses energy and emits some ionizing particles of radiation. The amount of source decays is called its activity rate. So if it has a high activity rate, it will release this radiation or particles more frequently. And then by doing this, it allows the nucleus to be at a lower and more stable state, which is what they all want. This is 2 pictures of cells that have been exposed to radiation. So overexposure can, this is a thing, cause cells to mutate and become cancerous. Just because you've been exposed to radiation doesn't necessarily mean you will get cancer. It's a possibility. So if you see A is healthy cells, whereas B is not healthy cells, doesn't look like that at all. Background radiation can come up, they can have a whole question on it, they have in the past. So, nuclear radiation is naturally all around us all the time, and it isn't just from man-made things, it is naturally occurring. So there's different types of background radiation you need to be aware of. So you have things like the majority comes from rocks. So radioactive decay of natural elements in rocks, such as granite, is 50% of our background radiation is from rocks. Radon gas is the one that's mainly formed through natural radioactive decay, and then that will fill our atmosphere. Food and drink, because they've been exposed to land, accounts for 11.5% of our background radiation. Ground and buildings, because they're made from rocks, accounts for 14% of our background radiation. You will not need to remember these percentages, by the way, so don't worry about that. Just be aware of the general allocation of the percentage. Cosmic microwave background radiation is naturally occurring as well in space. Nothing we can do. It's the radiation left around from the Big Bang explosion, and that accounts for 10% of our background radiation. And then we get on to the background radiation caused from human activity. It is only actually 14.3% comes from human activity, so not a lot at all. Medical, so hospitals accounts for 14% of that, So when patients get cancer treatments, X-rays, when you have radiotherapy, that accounts for 14%. Nuclear weapons testings and bombs is only 0.2% of our background radiation. And then natural disasters such as Chernobyl and Fukushima is 0.1% of background radiation, so not that much at all. Now, I've seen 2 exam questions in the past that have used pie charts in their radioactivity questions. Sometimes you have to use the data to come to a conclusion, other times you have to work out a certain percentage, okay? So just be aware of that. Here is an exam question, so if you wish to pause it now, you can. So it says the pie chart shows the sources of background radiation and the radiation doses that an average person in the UK is exposed to in 1 year. Radiation dose is measured in millisieverts. Other sources include nuclear weapons testings, nuclear accidents and power stations. So here we have radon gas, we have rocks and buildings, we have cosmic rays, food and drink, medical, including X-rays, and then we've got here another. So what is the radiation dose that the average person in the UK receives from radon gas? So it's only worth 1 mark, not a lot, but it can be the difference in the grade, we all know this. So we have here, you can see from the pie chart, radon gas here is 50%. Hasn't given us a value for this. What you have to do is add up all of these values. Now, in the past, I've seen people miss it out by 0.01 because they have missed this bit here. So that's quite a common mistake. So make sure you look really clearly. So you add all that up and the answer you get is 1.25 millisieverts. 1 mark, easy, but there's an easy mistake you can make there. They may also link background radiation to jobs or to travel. Now here I've got a list of people who may be exposed to background radiation, maybe in higher exposure than the average person. If you want to now, you can pause it, it's up to you. Decide which of these jobs would cause an increase in exposure and then rank them highest to lowest. So we've got cabin crew, radiology technicians, astronauts, baggage screeners, say in airports, nuclear weapons production facilities, mine workers, obviously that radon gas, physics teacher, and nuclear power worker. So this is the actual order. I mean, it's all your opinion really, but this is my opinion. So I would say astronauts first because they're in the sky. Exposed to radiation and cosmic microwave background radiation. Cabin crew, again, they're in the sky. Also, the radiant gas from the rocks is up there in the atmosphere. Mine workers are with the rocks with the radon gas. Radiology technicians, they are actually out the room when they do the X-rays, but they're then exposed to the patient afterwards when they're seeing them out the room who has just been exposed to the radiation. Baggage screeners, they're then touching the bags that have been through the X-ray machine. Physics teachers, I get radioactives out about 3 times a year, and all I have to protect me sorry, is a pair of rubber gloves. So I am actually exposed more than, say, the average person. Nuclear power workers have to be protected more, otherwise they'd have a high turnover of staff, they wouldn't be able to do it. And nuclear weapons production facilities, so they are really, really protected compared to other people. When it comes to radioactivity, there are 3 types of decay that we are interested in. They are alpha, beta and gamma. Now I suggest that you memorise this table because various questions will ask you information from this. Now an alpha particle, like we said before, is made up of 2 protons and 2 neutrons, same as the helium nucleus. It is a relatively large mass. It is, compared to the others, has quite a large mass. It would have a mass of 4, if you know anything about these symbols here. So 4 would mean it's got 2 protons, 2 neutrons, and this one means it's got 2 protons. So this would be the mass number, this would be the atomic number. So because it's got 2 protons, it has a relatively large positive charge and is actually the most ionizing type of radiation out of all 3, and I'll explain why that is in a second. Beta radiation is a very fast moving electron. Now what you may not know is this happens when a neutron inside of an atom randomly changes into a proton and emits an electron, okay? So when this happens, the number of neutrons will go down by 1 and the number of protons will go up by 1. So the mass number is not affected at all, but it will lose effectively, so gain a proton. It is less mass than an alpha particle because it is effectively just the mass of an electron, which is roughly 1 over 2000. We say it's negligible. Not that it has no mass, it has mass, but it's a negligible mass. It has a negative charge and it's less ionizing than an alpha particle. Gamma radiation doesn't have a mass, doesn't have a charge, because it's an electromagnetic wave. It has a very high frequency. We know it's the highest out of all of them. It doesn't have mass, no charge, and it's not that ionizing, but the problem we have is it can travel through a lot of things and it can travel a very long way. So you do need to know this table in depth. So I said that I was going to explain why things are the most ionizing. If you have a look here, we have an atom. You should all know the location of atoms from chemistry and from physics. We know we have the nucleus containing protons and neutrons, and we know that electrons occupy shells orbiting the the nucleus. So we've got here protons, neutrons, and electron. Well, an alpha particle is 2 protons and 2 neutrons, so it's effectively like this. This is relatively large compared to an electron. If this was to, say, encounter an atom, the chances of it hitting one of these electrons is quite high. Not really high, but it is quite high. So if it did hit this electron and knocked it off, it would cause it to become an ion. Beta radiation is just a fast-moving electron that gets emitted when the neutron turns into a proton. So the chances of an electron hitting another electron, not as high as, say, an alpha, but not impossible. Now, gamma has no mass at all. It's just a high-frequency wave, so it would need quite a lot of attack on an electron to cause it to become dislodged and knock it off of its location. So it's not that ionizing at all, but like we said, you're going to be exposed probably more to gamma than you would be to beta and alpha. So you need to know how far they can travel. Alpha can only travel a few centimetres in air, and it gets stopped by paper or skin. They do like to ask that in exam questions. Why is alpha no harm outside the body? Because it can't really get through the skin, but inside the body it can do a lot of damage. Beta can actually travel a few metres in air, but it will get stopped by an aluminium plate. And gamma can travel several kilometres in air. Comes from space, so yeah. And it gets stopped by meters of concrete or centimeters of lead. Will stop it also. So if you have a look here, I suggest that you learn this also. So although this is the most ionizing and can cause the most damage to us, it's not as dangerous because it can't travel that far. Beta, slightly more ionizing than gamma, but again, it gets stopped by millimeters of aluminium. Goes through paper, so it would go through skin. And gamma, most is stopped by, but some might still get through. So when it comes to these equations here, radioactive decay equations, they do like to put these through. I've got some we can get do in a second. You can pause this and read this if you want, but this first one we're going to go through is alpha. Now you need to balance it. It's an equation. You should know from chemistry all equations need to be balanced, which means you need the same amount of mass on one side as you do the other. Conservation of mass. Okay, so if you have a look at this example here, uranium 23892, which means it's got 92 protons, and 92 of that would be protons, the rest would be neutrons. It has then decayed here and emitted alpha. Now you can see alpha is losing 2 electrons, losing 2 protons and losing 2 neutrons. So by doing this, the mass number has decreased by 4, so it's gone from 238 now to 234. It loses 2 protons, so the atomic number has decreased by 2, and from 92 into 90. So here's a question, you can pause it now, from January 2013. So it says the decay of radon 222 can be represented by the equation below. Complete the equation by writing the correct number in each of the 2 boxes. 2 marks. So on this question, it's told you already it's alpha. So for this, you have to remember that alpha is 4 mass number to atomic number. So you can see here, the numbers you would put here would be, so it's gone by 2, 84, and the number you would put here would be 218. Such an easy 2 marks to get, but for it you need to remember alpha, 4 and 2. Beta radiation, you can pause and read this information if you want to. There's an example here. So for this, it's really important that you remember that a neutron has randomly changed into a proton. So by doing that, the mass number becomes unchanged because protons and neutrons both have the same relative atomic mass of 1. However, the atomic number, because we now have another proton, has increased by 1. So if we had carbon-14, an isotope of carbon, and it was going to emit beta radiation, you would get here no change in the mass number, but you would have this increased by 1. Now, going back to conservation of mass, if you have a look here, adding 0 onto this would make it 14 still. Minusing 1 off of 7 would put it back to 6. So that's another way that you can work on them. So here's an example here. Pause it if you want. So when this nucleus decays, it emits and changes into this atom here. So it says MO9942 goes to TC9943 plus radiation. What type of radiation is emitted? We see straight away the mass number is staying the same. The atomic number is increasing by 1, so it has to be beta. So here you would write beta radiation, give a reason for your answer. You could say any of those, mass number stays the same. You could say that the atomic number is increased by 1. There we go. You could also say a neutron has become a proton. Now you might say, where is gamma? They don't tend to put gamma questions on because gamma radiation doesn't actually do anything to the mass number or the atomic number. Gamma is a type of energy that's emitted. So when gamma is emitted alongside, it's usually done alongside other types of radioactive decay. If it emits an alpha particle, the new nucleus is left in a high energy state. So by releasing gamma radiation, it would allow it to come to a lower energy state. So there's no change for the atomic number or the mass number. Half-life is another one that everyone panics about and they do like to put on the exam. There is also another video clip on Mushroom Science about half-life. So they can give you it in 2 ways. They can give you a bit of information, a bit of text, or they can give you a graph like this. Now everyone panics about graphs. I love graphs. Graphs show you everything you need to answer basically. So here you have on the y-axis the activity rate. This goes up to 2000, and then you have the number, the time scale that it takes for this radioactive decay. It may be seconds, minutes, hours, days, years. It just depends what it is, what type of radioactive nuclei it is. This one's in years. So you can see this starts out at 2000. So if the half-life is the amount of time it takes for the radioactivity to decrease by half, or have half of the atomic nuclei, you would go down to 1000. Whatever this number is here, half it, go down to it. You then read across the graph until you reach the line, and then you will read down. This is where it can get tricky. I mean, on this one, it's not a very nice graph at all. Hopefully you'd have smaller squares, but this is where your error can occur if you do not read the graph correctly. Make sure you understand which every single little box is. So this one so happens to be 18 years. So the half-life for this is 18 years. Half-life for the radioactive nuclei will always be 18 years. So if you see here, again, I'd go down and I'd go to 500 because that's half of 1000. I'd read across again. Now, without even reading that, I would know that would be 36 years because 18 plus 18 is 36. Again, I go down to 250, read across, again, it would be another 18 years added onto that, okay? It's an exponential graph. It goes down because it will never quite get to zero because it's just halved and halved continuously. They have a higher activity rate at the start because obviously then it's releasing more, and as it becomes a lower energy state, it then starts to release less. So pause it here if you wish. This is a question from June 2015, and it did actually confuse quite a few people. So I'll go through it now. Okay, tritium is radioactive. After 36 years, only 10 grams of tritium remains from an original sample of 80 grams. Calculate the half-life of tritium and show clearly how you worked your answer out. Okay, so we have 36 years, 10 grams remains after that, and the original sample size was 80 grams. So if you say 80, apologies for the appalling writing here, divided by 2 would give us 40. Okay, so that would be 1 half-life. If we then said 40 divided by 2, it's supposed to be divided, not add, I promise you, equals 20, which would then give us our second half-life. If we then said 20 divided by 2 equals 10, and that's what we got down to. It wanted 10, okay, and that would be our third half-life. So it takes 36 years for that to happen. So you do 36 divided by 3 equals 12. So that would take us 12 years. So a little bit of maths, a bit of work for 2 marks, but it can really help. And here we see that was the answer, 12. Okay, 1 mark if you actually realise that it was 3 half-lives by showing that math. Uses of this radiation comes up ever so slightly, not much, but it's good to be aware of it. We actually use alpha as smoke alarms. So the most ionising radiation you actually have in your home. But it's fine because it only travels a few centimetres and gets stopped by paper or skin. So the plastic cover that's on it is more than adequate to stop the radiation. So the way it does this is like this. So the alpha radiation will constantly emit, randomly emit its radiation. By doing that, the air that is here would be ionized, which would produce electrons, and that would complete this little circuit here. So while this circuit is completed, the alarm does not go off. If some substance or some particles or smoke gets in between these 2 points here, it means that the radiation can't ionize everything, so it almost stops or blocks the electrons getting through. So by doing that, it will break the circuit, which then causes the alarm to go off. And it's really simple. You would actually need this to have a high activity rate and a long half-life. If it didn't have a long half-life, it wouldn't be emitting as much radiation, and then it wouldn't be ionizing as much, so your alarm would start to go off more and more. Beta is used in paper mills because it can go through paper. So the way they do it is they have a beta source, they have that going through the paper, and a detector. This will then have an automatic counter. So they will know sort of what amount of radiation they would need, the parameters, to get through for a certain thickness. If this number gets too high, that means too much beta radiation is getting through. If too much beta radiation is getting through, it obviously means this paper is too thin. That will tell the roller controllers to widen. If this number here getting through was too low, that would mean the paper was too thick, so the rollers would squeeze together a bit more. Again, you'd need a long half-life. Alpha is not suitable because it gets stopped by paper and a few centimetres of air, and gamma is not suitable because it would all get through anyway, so you wouldn't have a change really for the thickness of the paper. Actually can be used in aluminium factories as well. I've seen it used before, even though it gets stopped by millimetres of aluminium, but it can be used in aluminium making factories. Gamma radiation can be used in hospitals for radiotherapy. this one here is called a gamma knife, and the way it has it, you'd have the patient who unfortunately has a tumour, and this would rotate around the patient's head. Now, by rotating it around a certain pivotal point, so the tumour, for example, the tumour would always get the radiation, whereas the healthy tissue around the tumour would be limited to the dose of radiation. So it would be exposed, but it would only get a small dose, whereas the tumour would get a higher dose, and that will hopefully kill it. Gamma can also be used to sterilise medical equipment because it would kill bacteria. Now, the other things that come up regarding radioactivity is nuclear fission and nuclear fusion. They like to ask you the definitions of them, and they also like you to answer questions about them. So nuclear fission is when you get a larger nuclei splitting into smaller nuclei, okay? So it's a splitting of the atomic nucleus. It's when you have bigger ones into smaller ones. It's used mainly in nuclear reactors where we can make electricity. But here it's really important, larger into smaller. If you fire a neutron at it, because it's unstable, it causes it to split. So you think nuclear fission has two S's in it, so it goes into two smaller, or it has an S in it, so it splits, okay? This would be what we call a chain reaction. So by doing so, this larger nuclei goes into two smaller ones. That will then emit some neutrons. That will then hit other larger nuclei, which then splits into smaller ones. So it's a chain reaction that happens. It will release thermal energy and kinetic energy by doing this. And we use that thermal energy in nuclear power stations to then heat water that produces steam, which turns turbine, which turns generator and makes electricity. This is a question, you can pause it now, from June 2013. So it says the diagram shows nuclear fission process for an atom of uranium-235. Complete the diagram to show the fission process for chain reaction. This is 2 marks, and a lot of people go, I don't have a Scooby-Doo how to do this, but it's so simple. It's a chain reaction, it's basically repeating itself, so all you need to do is to copy what it already had. So it wants a neutron, will then hit another uranium-235 and split into these others as well. So it's already given you the answer right there. But people panic and go, well, I don't know how to do it. But just copy. It's simply just copy. So the answers here said that neutrons shown hitting other uranium-235 nuclei, and then the uranium-235 producing 2 or more neutrons. Easy marks to get. Most reactors we have use 235, some use plutonium as well. It splits it into 2 smaller nuclei, releasing 2 to 3 or more neutrons. They're absorbed by others, which then is a chain reaction, and it's quite self-sustaining. We would have control rods to limit it when we do it in nuclear power stations. Nuclear power stations come up mainly in P1, however I have seen them ask how to make electricity using them in P2, so it's something you need to be aware of. Nuclear fusion naturally occurs in stars, okay, not just the sun. It's when 2 smaller nuclei fuse together to make one larger, okay, so it's the opposite to fission. The way you can remember it is fusion has a U in it, so like the sun, okay. Well, fuse means to come together, to stick together basically. So you need to know that process. It generates a lot of heat energy. Well, the sun does it. It gives us all our thermal energy. And the products of fusion are not radioactive, whereas in fission they can be. We'd love to, in the future, be able to generate power using this. There are trials that go on now on a small scale. Massive advantages for it is it doesn't commit any carbon dioxide, but neither does fission, to be fair. And there's a large amount of energy, but there's no harmful radioactive waste like there is in fission. The sun's massive size and internal pressure is what creates the right conditions to be able to do this, so it's really hard to be able to replicate them in the lab, but like I said, they are actually trying. You need really high temperatures to be able to fuse nuclei. So remember the difference between fission and fusion. Fission is splitting and fusion is joining together. I hope this video has helped. Happy revising!